Okay, so for my video, I'm going to be talking about implicit differentiation. Most of the equations that we have been working with now are written in the explicit form, like y equals 3x cubed plus 7, where y is isolated by itself. However, for implicit differentiation, we sometimes will have equations written in implicit form. For example, 3x squared plus 9y equals 10. For this equation, it is written in the implicit form because you cannot isolate y by itself. However, there is a way to find the derivative still of this equation even without isolating y by itself, and that is using implicit differentiation. So an example that I have is x squared plus y squared equals 9. For this equation, you will just find the derivative of both sides, which is 2x plus 2y prime equals 0. And this y prime comes from finding the derivative of the equation with respect to x. So this can also be written as dy over dx. It equals y prime. So for this video, I will be writing y prime instead of dy over dx. So to continue with this problem, I will put all the terms that have y prime in them on the left and all of the terms that do not contain y prime on the right. So it's 2y prime equals negative 2x. Pulling out a y prime, because that is what we're trying to solve for, and you have y prime times 2y equals negative 2x. Isolating y prime, we're going to divide by 2y, divide by 2y, and you have y prime equals negative 2x all over 2y. That can be simplified to negative x over y. So the derivative of this equation is negative x over y, doing it implicitly. Now, another equation is x squared minus 5xy plus 3y squared equals 7. Again, in this equation, you cannot isolate y by itself, so to find the derivative, you have to use implicit differentiation. So I'll just find the derivative of every single term in this equation, left and right side. So you have 2x minus 5. You can factor out a 5 because it's a constant. However, now that you have x times y, you have to use product rule. So the derivative of the first, so the derivative of x is 1 times y plus the first, which is x, times the derivative of y, which is y prime, or dy over dx. It is the same thing. Plus the derivative of this term, which is 6y prime equals 0. The derivative of a constant is always 0. So I'm just going to multiply this 5 through. So you get 2x minus 5y minus 5xy prime plus 6y prime equals 0. Like I said in the example but before, you want to keep all the terms that have y prime on the left and move all the terms that do not contain y prime to the right. So you will have negative 5xy prime plus 6y prime equals negative 2x plus 5y. Factoring out a y prime from the left, you will have y prime times negative 5x plus 6y equals negative 2x plus 5y. Solving for y prime, you just divide by negative 5x plus 6y to both sides of the equation. Negative 5x plus 6y. So then your answer, y prime, the derivative of this equation, is negative 2x plus 5y all over negative 5x plus 6y. So that is how you find the first derivative of implicit equations like this one. Now I will show you how to find the second derivative of an implicit equation using implicit differentiation. An example is 2x squared minus y squared equals 3. Like we did in the first two examples, you're just going to find the derivative of this equation with respect to x. So this becomes 4x minus 2y y prime equals 0. Again, keeping the terms that have the y prime on the left, the ones that do not, moving them to the right. So now you have negative 2y y prime equals negative 4x. Factoring out a y prime of this term, you have y prime times negative 2y equals negative 4x. Solving for y prime, dividing by negative 2y, all divided by negative 2y. You have y prime equals negative 4x all over negative 2y. This can be simplified to 2x all over y. So the first derivative of this equation is y equals 2x over y. So now to find the second derivative, all you have to do is take the derivative of the first derivative to get the second derivative. Since this is quotient, you have to use the quotient rule, which is the derivative of the low times the high minus the derivative of the high times the low all over the low squared. So you have low d high, so y times the derivative of the high, this equals y double prime, minus 2x times the derivative of the low, which is y prime, all over low squared. Just going to factor all of these out. Y prime all over y squared. Seem to be stuck. However, even though we don't know what y equals or what x equals, we do know what y prime equals. It equals 2x over y. We can now substitute 2x over y in for y prime. So now we have 2y minus 2x times 2x all over y squared. At this point, it is just algebra. So now I'm going to multiply that through, and it will have 4x squared all over y, and this whole thing all over y squared. Now I need to create common denominators, so I'm going to multiply the 2y times y over y right here, and that will become 2y squared minus 4x squared all over y multiplied by 1 over y squared. That is the same thing as dividing by y squared, it's just easier to see. So at this point, what we are trying to do is to be able to substitute this 3 in for the original equation, because it should show up in the second derivative. So what can we do to manipulate this numerator to make it look like 2x squared minus y squared? We actually can factor out a negative 2. If we factor out a negative 2, you get negative y squared plus 2x squared all over, multiply the denominators together, you get y cubed. So to rewrite this to make this look like the original equation, you have negative 2 times 2x squared minus y squared all over y cubed. Now we can see that this equals this. So since we know that 2x squared minus y squared equals 3, we can substitute 3 in for this right here. Now it becomes negative 2, y double prime becomes negative 2 times 3 over y cubed. Just simplifying it, we find that the second derivative of this original equation is negative 6 over y cubed, and I hope that helps.